Okay, so I'm going to walk through some of the design decisions we made when we developed PyFR. The idea being to try and help motivate why certain things are the way they are in the code. So when you're reading the code and wondering why we did things a certain way, the idea is for this presentation to kind of make some of these things a little bit more clear and to get you into the same mindset that we were in when we were designing the code, so that when you're reading the code or trying to interpret some of its outputs, that you're in kind of a better place to understand why things are the way they are. Okay, at a high level, as I guess you all know, and as Peter kind of alluded to, performing large eddy simulations requires a lot of floating point operations. There really is nowhere around it. If you want to do a wall-resolved simulation, it's going to be expensive. But you may be thinking to yourself, well, the rate at which we can do floating point operations, so crunch numbers, increases in accordance with Moore's law. So roughly every 18 months or 24 months, we should expect our capability in this area to double. And you can see that at some level when new hardware is released. So NVIDIA currently have the V100, and very soon, as Neil talked about earlier in the day, we'll have the A100, which is a substantial improvement in terms of floating point capability. And so you may be thinking to yourself, well, what's the issue? Hardware is improving at an exponential rate. We have some good CFD codes, so why don't we just wait a few years for the hardware to catch up, and then we'll be able to do these relatively expensive simulations with the code we have just by buying a new cluster. And the issue there can be captured at some level in this plot. So what this graph shows is memory bandwidth in terms of megabytes per second for CPUs from 1994 until 2014. These are Intel CPUs. So the green line, in effect, represents how quickly you can move data on and off the chip. The blue line represents the rate at which that same chip can do calculations on this data. That's measured in megaflops per second, again from 1994 until 2014, observing that the y-axis is a log scale. Looking at this, it's quite clear that the rate at which we can do calculations on data has indeed increased at an exponential rate. That can be seen by the growth in the blue line. But the rate at which we can move data around, so we can shuffle it on and off the chip, has not increased at the same rate. Thus, if you were designing an algorithm or numerical method in the early 1990s, your view of the world would be that moving data around is inexpensive relative to doing calculations on that data. That can be seen by the fact that the green line is well above the blue line back in 1994. And so you would try and design your scheme in a way that minimizes the number of calculations that it needs to do for a time step. And that may be done by saving temporary data to memory so you can reuse it again later, or a whole other host of things that come in when you design your scheme. And indeed, if you look at the schemes employed by solvers such as Fluent, StarCCM+, or OpenFOAM, they're all using numerical schemes, typically second-order finite volume methods, that were really flushed out in their current form in the early 90s. And thus, these schemes are really designed in an environment where moving data was inexpensive relative to computing on that data. Moving to 2014, however, we see the trend is very different, in that performing calculations on that data is relatively inexpensive compared to the cost of shuffling that data around in memory. And so a scheme that was well suited to hardware back in the mid-90s is not well suited to hardware in 2014, and even less so today in 2020. And that's important, as everything around Moore's law that's really tracking the blue line, not the green line. And so if your scheme is limited by memory bandwidth, which is what OpenFOAM, ANSYS Fluent, and Star CCM Plus are, the improvement you're seeing from generation to generation is nowhere close to the improvement that will be predicted by Moore's law. Even more insidiously, if we look at latencies, so not overall throughput of the chip, but just how long does it take in terms of nanoseconds to do something. And we can compare a Pentium 4 from 2002, so a museum piece, against a 2016 Skylake i7 chip, which, due to Intel's ineptitude, is actually still relatively current in 2020. And what we can see is the time required to multiply two scalar numbers only halved in that period, going from about 2 nanoseconds to 1 nanosecond. And thus, all of the improvements that we saw in that blue line doesn't come from so much the chip itself, but from things such as vectorization, increasing core counts, and increasing vector lengths. And similarly, if we look at the time to access some data in main memory, just randomly, the time went from about 15 nanoseconds of latency down to 14 nanoseconds of latency. Basically, no improvement at all. And thus, even if you want your code to take advantage of the slight improvements that we've got in terms of memory bandwidth, it really needs to be able to take advantage of features such as vectorization and multiple cores, all of which put more pressure on the ability of an algorithm to scale. And thus, the conclusion is that while Moore's law does just about appear to be holding up, if you want to tap into that, you really need not just a different numerical scheme to what we have in the 90s, but a numerical scheme that is extremely well implemented, as accessing this performance that we have on these chips is non-trivial. And I guess the biggest takeaway from that is that, for the most part, all of the improvements we've seen in one way or another come from some form of additional parallelism. For example, on CPUs, we have multiple cores nowadays, each with a very wide vector unit. And so the parallelism is kind of exposed through 4 separate techniques. You've got MPI, which is generally regarded as under the categorization of MIMD. Then you've got SMT, so that's what Intel will call hyperthreading, where one core appears as multiple individual cores. Then at a slightly lower level, you've got the vector units on the cores, which can be pretty large these days, up to 512 bits on recent Intel and ARM CPUs, which again, you have to make use of if you want to get good flops or good memory bandwidth. That falls under the categorization of SIMD. And at the final level, you've got the fact that these chips can execute multiple instructions every cycle. And thus, you need some form of instruction-level parallelism in your kernel if you want to get good performance out of your code. So a very complex hierarchy that your algorithm and your implementation of that algorithm needs to be able to exploit. Then we have GPUs. So on the NVIDIA side, they have what they call streaming multiprocessors, each of which has some number of CUDA cores. And the overall parallelism is exposed through a technology that's known as SIMT, single instruction, multiple thread. So you've got a large number of threads all working in, at some level, lockstep with one another. Okay, so not only is it a challenging environment just in terms of the nature of the hardware itself and the manner in which you can get good performance out of it, but it's also the programming environment. And so CPUs are probably best programmed in OpenMP. NVIDIA, for their GPUs, wants you to use CUDA, and AMD wants you to use something between OpenCL or HIP. So there's no one easy way to write a code that works for all of the major platforms that we have today. And thus, even if you found an algorithm that works well, there's still the challenge of how do you implement it in a way that's maintainable and that allows you to target all of these pieces of hardware from one code base. And this is very much the problem that we set out to address with PyFR. And finally, we touched on this a little bit earlier today, is chips themselves are also becoming more heterogeneous. So if you look at a recent Intel CPU that you might have in your laptop, there are more transistors dedicated to the embedded graphics chip as there are to the actual cores themselves. And thus, even on small workstation class machines, there are reasons to want to take advantage of embedded GPUs and being able to use all of the capabilities of a chip. Hence, it's a very tough environment. So what are the implications of all of this just from an algorithmic standpoint? Well, firstly, to have a future in 2020, any algorithm that we consider implementing must be highly parallel, obviously, because our simulations are expensive and the chips are massively parallel internally. It must be able to conserve memory bandwidth, because memory bandwidth is the one thing we're not getting much more of. And finally, it needs to avoid indirection and mask latency, because as I showed in the table earlier, those latency numbers are not getting any better. They're very much just a fact of physics, and the speed of light doesn't appear to want to change. And so until it decides to do so, we'll have to live with it. With all of that, I would argue that for the unsteady compressible Navier-Stokes equations, and with some of our more recent research, even the incompressible Navier-Stokes equations, flux reconstruction is a very strong candidate from a numerical method standpoint for enabling practical large eddy simulations. But of course, there's still the question of how do we actually make it happen inside a code that people can download and run. As I guess you all know, since you're here and since you've been using it for most of the morning, our solution to this is called PyFR, which is our implementation of flux reconstruction in Python that is very much targeted towards modern hardware, where that typically is interpreted to mean GPUs, but also multi-core CPUs and Intel's various failed experiments they've had over the years. From a feature standpoint, I guess you've seen this table already, but if not, we currently support the compressible and incompressible Navier-Stokes equations using arbitrary order accurate flux reconstruction on mixed unstructured grids. So with a few caveats, we support all of the major element types. Primarily, in time, we use explicit Runge-Kutta schemes with automatic time step adaptation. We support single and double precision, pick whichever one works for your simulation. And we don't currently have any subgrid scale models. In terms of hardware platforms, in addition to CPUs and NVIDIA GPUs, which is what you've been using today in the workshop, we also support AMD GPU clusters. From which you might be asking, well, how do we go about this? How do we make this happen from a single code base, which, as I think Neil mentioned, is very much a novel aspect of our code, is the fact we can run across all of these hardware platforms just by changing a flag. So how do we do it? Well, the outer layer of PyFR, as I alluded to, is written in Python. Python as a programming language is very nice, it's very flexible, but it is not fast. Hence, our use of Python is just limited for setting up the problem and for things that aren't performance critical or performance sensitive. For the most part, the job of the Python layer is to read your mesh, read your input file, figure out what needs to be done, and then simply tell the hardware to call some sequence of kernels in the appropriate order, and that's pretty much it. Hence, Python is not being used for anything that's computationally intensive. It's just telling other low-level code what to do. Now, of course, then the question is, well, how do we get the hardware-specific kernels we need to run on these various platforms? Well, as Peter mentioned, in flux reconstruction, our operations can fundamentally be divided into two distinct categories of kernels. The first of these are matrix multiplication kernels, which for the most part handle data interpolation and extrapolation inside of an element. Hence, anything that shuffles data from one part of an element to another part of an element can typically be cast as a large matrix-matrix multiplication. And what I'm calling point-wise nonlinear kernels. These are things such as your Riemann solvers at an interface, computing the inviscid and viscous fluxes at solution points, etc. So
Freddie,
these are the two.
I think there's a question from Patrick.
Please.
He raised his hand. But...
it was a bit earlier about the features, but I just hold on the question until the end because it's a bit too late now. It's a bit off topic.
Sorry, Patrick, I missed you.
Yeah, no worries. No worries.
We'll certainly have time after this. And Ray, did you have a question? Or was your hand still up from before? Ray's put his hand down, I think. Right, I think you can go, Freddie. Yeah.
So we need two distinct types of kernels, matrix multiply kernels and point-wise nonlinear kernels. Well, matrix multiplies are a very well-defined thing. They're a convenient abstraction. Hence, it usually is not too difficult to find a matrix multiply routine for whatever piece of hardware you're running on. Although, as Peter mentioned, we do sometimes roll our own bespoke routines in certain circumstances where we know something special about the kinds of matrices. But at a high level, you can just view it as the hardware vendor will provide such a routine for us that we expect to be well-tuned and highly efficient. The question, however, is what to do about the point-wise nonlinear kernels, as these fundamentally encode the physics, and since they're nonlinear, they're difficult to abstract down into more fundamental building blocks. They really have to be coded directly. Hence, the solution we went for in PyFR is to use our own domain-specific language. The idea being that you write these kernels in our own internal language that's specific to PyFR, and these kernels are then translated at runtime into either C code, CUDA code, or OpenCL code. Once translated, the kernels can be compiled, and then finally, they can be invoked by the Python outer layer, and since they're hardware-specific kernels and are written in a low-level language, we expect them to perform very well. To give you an example, this is how the inviscid flux function works in PyFR. The language itself is called PyFR-Mako, as it's based around the Mako templating engine. And what's being shown on the left-hand side is how we write our inviscid flux function. This function is written in a way that's generic across dimensions, so it can work in both 2D and 3D from a single piece of code. And PyFR can then translate that into CUDA code, C code, or OpenCL code. To give you an idea of what this looks like, let's take the CUDA example. And what we can see is our relatively simple kernel on the left-hand side has got translated to something that looks, well, far less pleasant, shall we say. And that's all happened automatically. So PyFR has looked at the kernel, it's figured out what the parameters are, and then decided how best to translate that into a piece of CUDA code that will work well on NVIDIA hardware. To give you a couple of specific cues into this kernel, the first thing we'll note is that this PyFR Mako language hides the data layout from whoever's writing the code. So on the left-hand side here, we say FPD type T, which is typically single or double. Inv-row, which is just a variable, is 1 over S0. So we're computing the reciprocal of the density. Very nice, very simple. The density is just by rote, the first element at each solution point is just the density. So that's how we normally write down the Euler equations, and we're taking the reciprocal of it. However, what we can see here on the right-hand side is that this simple indexing scheme has translated into something quite a bit more obscure, shall we say, when it's actually been turned into CUDA code. The key idea being that whoever is writing PyFR Mako code does not need to have any specific insight as to how data is actually arranged in memory on the device. We're therefore free to pick the best memory layout for any piece of hardware without the developer needing to concern themselves with these specifics.
Just a quick question there then. I would nearly describe this as automatic code generation. Would that be fair to say?
Yes, it falls under the category of automatic code generation.
And would this be as efficient as a code that if somebody came along, if you had somebody that could write CUDA directly or C directly, would the code that comes out of the Python script be just as fast, or is there a penalty that you pay there for the automation?
There's no specific penalty in terms of individual kernels, although if you're writing the kernels yourself, some things might be a little bit easier, such as merging kernels together, etc. But in terms of a blow-by-blow comparison, the kernels that we get out of this translation scheme perform exceptionally well in terms of those that are limited by memory bandwidth typically go on to achieve a very high percentage of peak memory bandwidth. So in an absolute sense, they're performing exceptionally well. And we've done measurements in that regard.
Okay.
The second thing to note is that the templates that are kind of passed through this PyFR Mako language can depend on runtime parameters. An example here that I've got is one called NDIMS, which is the number of dimensions in your simulation, which you already know when you actually start running the code and seeing if the mesh has triangles and quads or hexes, prisms, pyramids, and tetrahedra. So that ends up in this NDIMS variable, which then gets substituted at runtime when the code is being generated. In this case, for this example, NDIMS was 2, and so you can see that that NDIMS piece has been substituted for the number 2. Secondly, we can use Python to generate code. So on the left-hand side here, we have a Python for loop. It's a double loop over NDIMS by NDIMS. And on the right-hand side, we can see that's expanded out to 4 lines of code, this being the core bit of the momentum fluxes for Euler's equations. And again, this cuts down the amount of hand writing and hand tuning you need to do, as it's just completely automated and allows the same set of kernels to work in 2D and 3D. Now, a key thing to note about the domain-specific languaging approach we have taken in PyFR is it only implements the functionality which is actually required by PyFR, and that we are confident can be translated efficiently across all of the platforms we support. This means the language is somewhat more limited than one might expect, but the idea here is that we don't want to have functionality that we don't use, as that functionality tends to go untested. It may become broken or may not perform well. So we only implement what we need, and everything we implement, we are extremely confident will work well across every single platform. And this makes it a lot easier to develop code, because if you can do it using our domain-specific language, you can be reasonably confident that it's going to perform well, and you won't need to spend time tuning it or doing extensive early testing on every piece of supported hardware. This architecture is what enables PyFR to be performance portable across a range of platforms. So not only can we run on all the aforementioned pieces of hardware, but we can run efficiently. There are lots of codes and lots of finite element frameworks that have some level of GPU support, although when you dig into it, it may be that the performance on GPUs is not what you would expect by looking at the hardware specifications. That's definitely true if you look at the GPU support in a code such as ANSYS Fluent, where although it can run on them, the performance benefit you get really is below what one would expect. Or alternatively, some codes do have GPU support, but all of the features you might want to actually use in a real simulation are only supported on CPUs. A good example of this in finite element libraries is the only algorithm they support for solving linear systems on GPUs is the conjugate gradient method, and if you want to do anything fancy such as preconditioning or multigrid, you're back on the CPU. Whereas with PyFR, through this design, we have complete feature parity across all platforms. So every single feature is supported on every single platform, and it's supported well. And finally, as we talked about a little bit earlier this morning, this architecture with performance parity allows us to mix and match different PyFR backends across MPI ranks, as the MPI rank doesn't care how another MPI rank decides to compute its right-hand side or evaluate its data. All it cares is that it's got a buffer that it can exchange. And thus, with that, in PyFR, we have the ability for heterogeneous computing, which is, again, a piece of functionality that we're quite proud of and think will become more important in the future as more vendors begin offering their own piece of hardware and people just want to be able to run on any free piece of hardware that are available. However, one downside to this approach is that anything that's very different or to what we've done previously within PyFR in terms of functionality typically requires us to either develop or extend the domain-specific language to add in that new functionality, or write some degree of platform-specific code for each individual backend, because we can't rely on the domain-specific language to do it. So that's one of the downsides, is that when it does come to adding new functionality, it can sometimes require a little bit more work and require you to look at the domain-specific language, or alternatively, write some platform-specific code if you don't feel that it can be extended efficiently. So that's one of the trade-offs that we have in PyFR for insisting on feature parity and performance portability, is that doing new things can sometimes require a little bit of thought. But the benefit of putting that thought in is once you've done it, you can be reasonably well assured that whatever you do will work well everywhere, including future architectures that we may decide to port PyFR to.